The gradient of a line is a measure of how steep that line is. We may have a very steep line like that, and the gradient will be larger than a line which is a bit more shallow. So lines that are fairly shallow, like this one, will have fairly low, fairly small gradients. Steep lines have large gradients. And lines which are horizontal will have zero gradients. And we need to try to quantify that a little bit, try and do this a little bit more mathematically, so we can actually measure how much steeper this is than this one, and so on. I've drawn 3 line segments on this diagram. Let's just look at them. The first one is the line segment from A to D. Now, as we move from A to D, the x-coordinate increases from 1 to 2, and the y-coordinate increases from 1 to 5. Now, the line segment AD is steeper than the line segment AC. As we move from A to C, x changes from 1 to 2, and y changes from 1 to 3. And AC, in turn, is steeper than the line segment AB. The line segment AB is, in fact, horizontal, because as x increases from 1 to 2, the y-coordinate doesn't change at all. It remains at 1. Let's try and think about why, mathematically, the line AD is steeper than the line AC. And the reason for this is that in both cases, our x-coordinate is changing from 1 to 2, but as we move from A to D, there's a much bigger change in y than if we move from A to C. So it's this relative change in y, relative change in x that's going to be important. What we do is we calculate the change in y and divide it by the change in x. That's going to be a measure of the steepness. Let's do it for the point AD, for the points A and D. Okay, as we move from A to D, y changes from 1 to 5. So the change in y is 5 minus 1, and the change in x, well, x changes from 1 to 2, so the change in x is 2 minus 1. So this quantity, the change in y over change in x, for the line AD is 5 minus 1, which is 4, 2 minus 1, which is 1, and 4 over 1 is 4. So that's a measure of how much y changes as x changes from 1 to 2. What about the segment AC? Let's do the same thing. Well, the change in y now is from 1 to 3. So the change is 3 minus 1. The change in x, well, x goes from 1 to 2, so the change is 2 minus 1. And again, 3 minus 1 is 2, 2 minus 1 is 1, and 2 divided by 1 is 2. So this is a measure of the relative change in x and y. What about AB? Well, as we move from A to B, y doesn't change at all. So the change in y is 1 minus 1, which is, of course, 0, and the change in x is still 2 minus 1. So we get 0 over 1, which is 0. So you see, this quantity, change in y divided by change in x, gives us a measure of the steepness of these lines. As we would expect, the change in y over change in x for AD, which we turned out to be 4, is greater than the change in y over change in x for AC, because AD is steeper than AC. And in turn, this change in y over change in x for AC is greater than the change in y over change in x for AB, because AC is steeper than AB. So it's this quantity which gives us the measure that we're looking for. And it's this quantity we define to be the gradient of the line segment. We often use the symbol m for gradient. So the gradient is defined to be the change in y divided by the change in x as we move from one point to a neighbouring point. Let's do that for some general case. Suppose we have a system of coordinates, a point A, x1, y1, and a point B, x2, y2. And we're interested in the gradient of the line segment joining A and B. Let me put in a horizontal line through A and a vertical line through B. So there's my x-axis, there's my y-axis. As we move from A to B, x changes from x1 to x2. Y changes from y1 to y2. So the change in y divided by the change in x, well, the change in y is the final value minus the initial value, so it's y2 minus y1. The change in x is x2 minus x1. And that is the formula that we can always use to find the gradient of the line joining 2 points. We can think of this another way. Suppose we look at this angle in here. Let's call that angle theta. Now the change in y is just this distance here, the distance in there. And the change in x is this distance in here. And if we take the change in y and divide it by the change in x, what we actually get is the ratio of this side of this right-angled triangle to this side. And that's just the tangent of this angle here. So this quantity that we've calculated is not only the gradient of the line, it's also the tangent of the angle that the line makes with the horizontal. So the gradient m, which we've said is y2 minus y1 over x2 minus x1, is also equal to the tangent of theta, where theta is the angle that the line makes with the horizontal. We can take this a stage further. Suppose we continue this line backwards until we meet the x-axis. Then this angle in here, between the extended line and the x-axis, corresponds to this angle here. These are corresponding angles, so this too must also be theta. So in other words, the gradient of the line is also the tangent of the angle that the line makes with the x-axis. Let's have a couple of examples. Let's choose a couple of points. Supposing A is the point 3, 4, and B is the point 8, 14. Let's calculate the gradient of the line joining these 2 points. Well, the gradient is simply the difference in the y-coordinates, 14 minus 4, over the difference in the x-coordinates, 8 minus 3. 14 minus 4 is 10, and 8 subtract 3 is 5. And 5 into 10 goes twice. So the gradient of this line is 2. Let's take another example. Suppose we have the point A, which now has coordinates 0, 4, and B, which has coordinates 5, 0. Let's do the same calculation. The gradient will be the difference in the y-coordinates, that's 0 minus 4, divided by the difference in the x-coordinates, 5 minus 0. So this time we'll get minus 4 on the top, 5 at the bottom. We get minus 4/5. So this is a little bit different now because we've found that we've got a negative number for our gradient. Let's see what that actually means. Let's plot the points and see what's going on. Point A, 0x coordinate, y coordinate of 4, so let's put that there. That's point A. Point B has an x coordinate of 5, that's there, y coordinate of 0. So there's my point, there and there. And the line joining them looks like this. And we know that this line has gradient minus 4/5. This line, as you notice, is sloping downwards as we move from left to right. And that's why the gradient turns out to be negative. Another way of thinking about this is that the angle that the line now makes with the x-axis, this angle in here, this theta, is now an obtuse angle. It's greater than 90 degrees, less than 180 degrees. So we have an obtuse angle, a line which is sloping downwards from left to right, and a negative gradient. Let me try and summarise all that behaviour. If you have a situation like this, where the angle that the line makes with the horizontal is acute, then the gradient will be positive. And the reason for that is that as you move along the line, as x increases, y also increases. So the change in y and the change in x have the same sign. It's also important to recognise that if we take the tangent of an acute angle, you get a positive number. So tan theta, which we know is the same as m, is also positive. What about an angle that's sloping, a line that's sloping downwards? We know that the angle is now theta and it's obtuse. We know that the tangent of an obtuse angle is negative, and as we've seen, the gradient is negative. And that's because as x increases, y is decreasing. So the change in y and the change in x have different signs. So when we take the ratio, we'll find out that the gradient is actually negative. And finally, let's have one where theta is 0. So the angle that the line makes with the horizontal is 0. Well, tan theta is 0. So that's consistent with our intuition that tells us that m is 0, the gradient's 0. Let's have a look at some parallel lines. Here's a line. Let's call it L1. L1 will make a certain angle, theta 1, with the x-axis. So its gradient, as we've seen already, is tan theta 1. M1, its gradient, is tan theta 1. Let's put another line on that's also parallel to this first line. This line is L2. It'll have a gradient M2. Let's extend it back to the horizontal axis, and let's measure this angle. That will be theta 2. And M2 will be the tangent of theta 2. Now, because these two lines are parallel, they cross this x-axis at the same angle. Theta 1 and theta 2 are corresponding angles, so theta 1 must be equal to theta 2. So because theta 1 is theta 2, tan theta 1 will equal tan theta 2. So in other words, M1 equals M2. So for two parallel lines, as you might have expected intuitively, the two gradients are equal. And conversely, if we have two lines for which the gradients are equal, then we can deduce from that that the two lines must be parallel. Okay, so that's parallel lines. Let's look at some perpendicular lines. See if we can deduce something about the gradients of perpendicular lines. Start with a point P and the origin there. And let's suppose point P has coordinates A, B. That means that to get to P from O, we go a distance A in the x direction and B in the y direction. Now what I'm going to do now is I'm going to draw a perpendicular line, a line that's perpendicular to OP. And I'm going to do that by taking OP and rotating it through 90 degrees. So the point P will move around here and it will move to a point up there somewhere. And let's call that new point Q. And we're going to try and figure out what the coordinates of Q are. This angle in here is 90 degrees because OP and OQ are perpendicular. Now to get from O to P, we had to go horizontally a distance A and vertically B. So if this triangle shifts round over here, to get from O to Q, we'll have to go vertically a distance A and then horizontally a distance B. So you see we've just shifted this triangle, rotated it round through 90 degrees. And doing that, we can then read off the coordinates of point Q. Q will have an x-coordinate of minus B and a y-coordinate of A. Let's now calculate the gradient of the line OP. Let's call that MOP. Now MOP, remember, is the change in y divided by change in x as we move from O to P. As we move from O to P, the change in y is B minus 0. The change in x is A minus 0. So the gradient of OP is just B over A. What about the gradient of OQ? Let's call that MOQ. We want the change in y divided by the change in x as we move from O to Q. Well, the change in y as we move from O to Q is A subtract 0, and the change in x is minus B subtract 0. So this time, this simplifies to A over minus B, or minus A over B. Now let's see what happens when we multiply these two results together. Let's take MOP, and we're going to multiply it by MOQ. That's B over A multiplied by minus A over B. And you see, when we do that, the A's cancel, the B's cancel, and we're left with just minus 1. This is a very important result. If you have two perpendicular lines, then the product of their gradients is always minus 1. And correspondingly, if you've got two lines and you find that when you multiply their gradients together you get minus 1, you can deduce from that that the lines must be perpendicular. Let's just have a look at an example. Let's have 3 points. Supposing A is the point 1, 2, B is the point 3, 4, and C is the point 0, 3. And we'll ask ourselves the question, is AB perpendicular to AC? That's the question. Is AB perpendicular to AC? Well, we'll do this by calculating the gradient of the line from A to B. Let's call that MAB. And then we'll find the gradient of the line from A to C, and we'll call that MAC. So let's do this calculation. We want the gradient of the line from A to B. Well, that's simply the difference in the y-coordinates, 4 minus 2, over the difference in the x-coordinates, 3 minus 1. 4 minus 2 is 2, 3 minus 1 is 2, so the gradient of AB is 1. What about the gradient from A to C? Well, the difference in the y-coordinates now is 3 minus 2, and the difference in the x-coordinates is 0 minus 1. So we've got 3 minus 2 is 1, 0 minus 1 is minus 1, so all this simplifies to just minus 1. If we multiply the two gradients together, MAB multiplied by MAC, we'll get 1 times minus 1, which is clearly minus 1. So the gradients of these two lines multiplied together have a result which is minus 1, and that means that the two lines AB and AC indeed must be perpendicular.